All right, so now we are on the last part of 2.6, which is looking at slant asymptotes. Again, this is a very specific situation that has to occur in order for a function, a rational function, to have a slant asymptote. So for any rational function, if the degree of the numerator is exactly one more than the degree of the denominator, then the graph of the function has a slant or oblique asymptote. Using long division or synthetic division, the equation of the slant asymptote can be determined. So this question just wants you to find the slant asymptote. It doesn't want the vertical, doesn't want any of the other stuff. And so first thing we should do is just verify that it will have a slant asymptote. The degree in the top is 2, the degree in the bottom is 1. So it's exactly 1 bigger. So if we did synthetic division, which we should remember how to do. So because it's x plus 1, remember, it's going to be a minus 1 on the outside. And on the inside, we got a 1 for a coefficient of x squared. Our x term has a negative 1, and our constant is 0. So now we could try to do this differently, but in this case, it's going to be just as fast either way. So if we do our synthetic division, and we got a positive 2, 2. So remember, what does this tell us? That means we can rewrite this in a different way using a quotient and a remainder. So in this case, remember, this is our remainder, this is our constant, and this is our x coefficient. So this should be equal to x minus 2 plus our remainder. And our remainder, remember, we have to put it over the divisor. So in this case, it would be 2 over the x plus 1. Now, if we want the slant asymptote, we actually have the equation right here. It's this first part. Our slant asymptote has to be the equation of a line. So if we wanted our slant asymptote and we do our synthetic division, whatever that linear component is, that should be the equation of our slant asymptote. Now, just to check, let's maybe do it on our graphing calculator just to see. So if we turn this on, we can clear this out. So let's use parentheses just to be absolutely careful. So x squared minus x all over x plus 1. And so if we graph it, you can kind of see that if we sketched in a line here, it would be an asymptote. The graph would never touch it on either part, but it gets really, really close to it. And the equation of that will be of the form x minus 2. So when we can see the y-intercept here of negative 2, and you know, it just would get so very close to it on both sides. Again, not the greatest of graphs, but at least it gives you an idea of what it looks like. So, and the other thing obviously of note is we do have a vertical asymptote. I mean, we can tell by the bottom it's equal to 0 at negative 1. So if we drew a vertical line at x equals negative 1, again, the graph's going to get really, really close to it, but it should never touch it. So that's all that problem wants. So just, again, be careful. Don't dig too deep into getting all the information, especially when they're not asking for it. So all they want is the slant asymptote, and there it is. Done. Now, this last problem has a lot of layers to it. So for the following function, state the domain, identify all intercepts, find any vertical or slant asymptotes, and plot additional solution points as needed to sketch the graph of the rational function. All right, so this has got a lot of layers to it. But before we get too deep into it, we want to be a little bit careful about, any common factors between the top and the bottom. So we'll take care of that in a minute, but we can do the domain. So remember, the domain is really just based off of the bottom. So if we set the bottom equal to 0, well, so the domain, I'll just set it up. So x squared plus 3x plus 2, we can factor this. So we get our 2 zeros for the bottom. But remember, those are going to be where vertical asymptotes could possibly lie. And again, because we haven't checked to see if there's any common factors yet, we can't say that these are vertical asymptotes. So, and we'll see that in a second. But let's finish off our domain. So remember, we had to go from negative infinity to the first 0 we interact with on the bottom. And negative 1 to infinity. So that should be our domain. Identify all intercepts. Well, this is going back to the beginning a little bit. So how did we find intercepts? Now we might need more paper here, so I might dig out another sheet, but we'll fit as much as we can on here. So identify those intercepts. Well, I'm going to go up here. So if we wanted to find y-intercepts, remember, that's when you let x equal to 0. So now I'm just going to write it as y. F of x and y, we can interchange that. So that's okay. But if we let x equal to 0, look at what happens. All these things are going to disappear. So all we have left on top is 1. And when we let the bottom equal to 0, all those disappear either also, and we're left with a 2 on the bottom. So that means we're going to get 0, 1/2. Okay, so let's do our x-intercept, which we know lets y equal to 0. So if we put the whole rational function equal to 0, that's what we are starting with. But because it's a fraction, how does a fraction equal 0? Only when the top's equal to 0. So the bottom is irrelevant. So all we really care about is making the top equal to 0. So if we make the top equal to 0, well, I think we might be able to do a little bit of factoring on that. We can do some factoring by grouping. Now, I like my 0 on the other side, so I'm just going to flop this around. So all we care about is setting the top equal to 0. I think we might be able to do some factoring by grouping. So if we group together the first 2 and the second 2, we can pull out an x squared. And we should be left with 2x minus 1. We factor out a negative because the signs are backwards. Let's factor a negative out, negative 1. That's going to leave us with 2x minus 1. Okay. So now we can do a little bit of grouping. And we have a nice quadratic that we can factor as well, if we wanted to. But I think we can do it without it. So we just got to be careful that we do get a plus or minus 1 And then in the other case, we get x is equal to 1/2. So it looks like there could potentially be three x-intercepts. So now we're going to have to verify it, but right now we got -1, 0, we got 1/2, 0, and then we got 1, 0. Now, why can't we just say that all three of them are x-intercepts? Well, because we didn't check to see if the top and bottom had any common factors. And if we kind of look back here a little bit, we have the factorization for the bottom as x plus 2 times x plus 1. Now, had we factored this a little bit more, we would have seen that this is x plus 1 times x minus 1 times 2x minus 1. And so there's the problem. We have a common factor of x plus 1. So those are going to cause a little bit of issues there. So when we plug in x equal to -1, it's going to cause the bottom to be equal to 0 as well as the top equal to 0, which is no good. So that means that this is not going to be an x-intercept because the point doesn't exist. So that's the problem with that one. So we really only have 2 x-intercepts and just the 1 y-intercept. Okay, so that was part A and B. Part C is to find those vertical or slant asymptotes. Now, because we have this information about the domain, we can kind of cheat now and identify those vertical asymptotes. So the vertical asymptote, we already said that x equal to -1 is no good. So that's gone. So the only possible candidate would be x equal to -2. That's the only vertical asymptote in this case. Now, as far as the slant ones, well, I think I might have some room on the next page. Let's use that. So now let's write down the function again. So we had 2x cubed minus x squared minus 2x plus 1 all over x squared plus 3x plus 2. Now, what's nice is if we wrote this in factored form, just so you can kind of see those issues. So we said this was x plus 1 times x minus 1 times 2x minus 1. And this was x plus 2 times x plus 1. Now it's even more clear why there's a problem. You can see that there's a common factor in the top and bottom. And, you know, could we just cancel those out? Yes and no. There is some importance to keeping those in there, and we'll see it when we actually graph it. But for now, let's just kind of leave those in there. Yeah, it's hard to erase it, but you get what I'm trying to do. But where did we leave off? So we already had the vertical asymptote of x equal to -2. Now, we can see that this should not have a horizontal one because the degree in the top is bigger than the bottom, but it does have a slant asymptote because the degree in the top is only 1 bigger than what's in the bottom. So if we're trying to find those slant asymptotes, we're going to have to use long division since we don't have the ability to do synthetic division with this type of rational function. So let's set up our long division. And see what we get. So to start it off, it looks like we can use a 2x. So 2x cubed plus 3x squared plus 4x. And now we got to subtract. So if we subtract, our x cubes are going to disappear. We're going to get a minus 3x squared and a minus 1x squared. So that's going to be a minus 4x squared. And we'll have a minus 4x and a minus 2x is a minus 6x plus the 1. And so now we're going to have to get a minus 4. So that'll give us a minus 4x squared minus 12x minus 8. And we got to subtract those. So our 4x squares, our negative 4x squares are going to cancel. So we'll have a positive 12x and a minus 6x, which is a positive 6x. Positive 8, positive 1 is positive 9. And we're done. We can't divide any more. So again, we could rewrite this polynomial now as our quotient plus our remainder. So as far as our slant asymptote, remember all of this is irrelevant. And we can kind of see that now if we apply that technique for those horizontal asymptotes. When the power in the top is smaller than the power in the bottom, the whole thing goes to 0. So remember, it approaches y equals 0. So this is essentially 0. So our slant asymptote should just be the first part. So now we have the bulk of what's been asked of us. So we have our domain, we have our intercepts, we've identified the vertical and slant asymptotes, and so now the last thing to do is plot additional solution points as needed to sketch the graph of the rational function. So let's just make sure we have a visual of everything. So 0, 1/2, and we got my head in the way of 1, 0. We have a vertical asymptote at x equals -2. We have some zeros in here. So we got a lot of information to go off of. Now, as far as your graph, again, it's not a perfect drawing, but we want to try to get a little bit accurate if we can. So we'll draw it fairly big. Now, as far as the y-axis, I'm not going to draw that in just yet. Let's just start with all the other information. So we know we have a 0 at 1, 0. We also have a 0 at 1/2. We had a problem, remember, at x equals -1, which we'll see in a minute. But we had a vertical asymptote at x equals -2. Now, as far as the slant asymptote, remember the slant asymptote was y equals 2x minus 4. So we can graph that in here. So we have a point here. Now again, the slant asymptote isn't a hard line. It's another dotted line like this because it's not anything that is graphed. It's not part of the function itself. So, but we can use some reference points. And I think I got a ruler in here even. So we can even just kind of sketch that out. So there is our slant asymptote. All right, so now as far as drawing the rest of this, well, we can kind of see that there's a little wackiness going on here. But as far as the x equals -1, again, we should probably plot a few points in here. Now, if we wanted to set up a table, we could. And it might be even easier if we use the graphing calculator to get some of those key points, some of those other points. So let's maybe use that to our advantage. So we'll clear that one off, and we'll put in our rational function. So 2x to the third minus x squared minus 2x plus 1 divided by x squared plus 3x plus 2. And so if we get a table, now we don't have to draw every single point, but we can kind of see what happens. You know, if we put in -1, we see right off the bat there's an error. And we expected that because the top and bottom are equal to 0, so there shouldn't be anything going on at that point. But what happens around it? Well, we know what happens when it gets closer to -2. So, I mean, if we said -1.99, we can see we get a really large value of y. So it's kind of going up towards infinity. Now, let's see what happens close to -1. So let's try a -1.1, just a little bit to the left of it. And so we get roughly 7.5. So if we said -1.01, -6. So it looks like it's getting really close to 6. It's never going to quite reach it, but at least we know what's happening close to that that value of x. So, you know, so if we had this was 6, basically what's going to happen is there's going to be an open dot at -1, 6, and this is going to kind of go up off to the infinity. And so now we got to find out what's kind of happening in here. And I'm almost thinking it's going to kind of cut through and hook up. Now the one thing we didn't write down was the y-intercept. Now the y-intercept was 1/2. So somewhere in here. So I think that really lends more credence to what's happening. It's going to just tuck underneath the x-axis and then kind of go up off this way. Something like that. Not perfect by any means. It might go lower or something, but this is a rough sketch. So that's that part. Now what's missing is on the left side of -2. On the left side of -2, well, let's see what's happening. Let's use our graphing calculator again. So if we said -3, well, it's 28. All right, well, let's try -2.5, -42, right? -2.1. And we can see it's getting larger and larger on the negative side. So our graph really isn't going to be big enough. I almost drew it too big to be able to see the full picture. But let's do a few more points here. How about -2.001? Let's get really close to that. X equals -2. And we can see it gets really, really large on the negative side. So just like this one was going up to infinity, on the other side, it's going down to -infinity. So, all right. And now the other part of it to remember is that it's approaching this line. So let's let the cat out of the bag. let's see what it looks like. So we have that part of it there, but the rest of it is not visible. Why is that? Well, let's maybe affect our zoom. Let's zoom out a little bit and see if that does anything. Ah, there it is. So you can see that there's that line, that slant asymptote of y equals 2x minus 4, and we have a vertical asymptote in there. And this point here is never going to be seen on a graphing utility like this. It's just not possible. Because it gets so infinitely close, you're never going to see an open dot on there. But it is important to make note of. So you should have that in your graph. So, all right, well, that is the end of this section. This is a very, involved case. So, using a graph utility to kind of get a sense of what the overall look is good, but then you also want to be careful about these little specifics when they happen. So, hopefully that was informative for you, but if you have questions, definitely let me know. Alrighty, that wraps up this section, and we'll see more of the next unit, which we jump to chapter 4, trig. So, see you then.